the energy of universe represented by this square, and part of it, the system, that we had special interest in it. Everything out of the system, we call it surroundings. So that energy of universe is conserved, means if there is any exchanging of heat or matter, especially we are talking about energy right now, if there is any certain exchanging between system and out toward the surroundings, it should be totally conserved. Part of the universe system, we can simply measure its energy by using the apparatus that we took it last time, and we called it calorimeter. It's isolated system supported by thermometer in order to study change of temperature. If it's closed, like what's given previously, means pressure is constant. If the pressure is constant, by referring to amounts of energy, it's equal to Q as a heat plus the work. Work are going to be measured here by using the pressure and change of volume. If the pressure is constant, it means it doesn't change. If it doesn't change, this part of equation going to be zero out of the calculations. So simply, guys, energy of the system, it's represented by heat in a constant pressure. Heat in a constant pressure of the system, we call it enthalpy of the system, or the heat content of the system. Heat of system, it could be measured within all processes or reactions, during all kinds of reactions or changes. Heat or enthalpy of vaporization, heat or enthalpy of a fusion, solution, bond formation or dissociation, both are the same. Neutralization in acid-base reaction, ionization energy when one electron is removed. So within all reactions and processes, the enthalpy could be measured here simply. Enthalpy of all substances or majority of substances is measured, so that we are concerned about standard enthalpy of formation of substances. Formation of substances is abbreviated by delta HF at standard conditions. It is heat needed or released in formation process of substances. Needed or released, if you remember, exothermic, it is heat released, and endothermic, it's heat needed. Released, it's represented by negative amounts of energy, negative X kilojoule. And if it's needed, it's abbreviated, or it's represented by positive X amounts of energy by kilojoule unit or kilocalorie, whatever. So that heat of each substance at each state is tabulated and measured. So, for example, by referring to tables here, it's a part of plenty of tables, substance and heat of formation of each compound or each substance or each element. For example, hydrogen, when it's H plus at a gaseous state, the heat of formation of this case is 1536 kilojoule. All of those kilojoule per mole. So that the original case of hydrogen, it's hydrogen H2, and it's a neutral. It's turned to H plus by removing one electron. So we call it heat of ionization, if you remember. Removing one electron from gaseous state, from atoms in gaseous state. Here it's positive. Positive means needs this amount of energy. H2 in a gaseous state, H2, it's the natural state of hydrogen. Nothing happened. Automatically, we could find H2 like a gas and its diatom nature, so that zero amounts of energy are consumed. It's the ordinary case of hydrogen. Lithium, the original case of lithium, it's single bond in solid state. So the original case, it's zero. Nothing consumed, nothing released. Ordinary case of lithium in nature, it's zero. But if lithium loses one electron in ionization, it needs this amount of energy. And also, if lithium is dissolved in water, aqueous, AQ, it means lithium, when it dissolved, it releases this amount of energy. So each case, each state of ionization, it has a special amount of formation. And all of those cases and the rest of elements and many compounds are measured and tabulated, so that we could apply enthalpy of formation in order to find enthalpy of reaction. How could we find it? Actually, as any kinds of energy, it could be measured like change on heat or enthalpy, if you want. It's equal to the final state minus the initial state. Final state in reactions, it's the product, and the initial state, it's the reactant. So that heat of reaction, it's equal to the product or enthalpies of the product minus enthalpies of reactants. Here we have enthalpies of formation of each component by referring to the tables. And each one of those is given in terms of kilojoules, the unit, kilojoules per 1 mole. If you want to find heat of reaction here, it's equal to the summation or the total of products minus the total of reactants. So that here the products minus reactant, and keep it in your mind, that's related to 1 mole of materials. So if it's 2 here, this amount it's going to multiply by 2, and the rest of those components are 1 to 1 to 1, so we're gonna take it as it is. How could we write it? It's equal to the product here, it's negative 319.2, and it's added to negative 285.8. Here is the products, enthalpy of products, minus the first one here, it's 2 times negative 45.9, and it's the first component added to the last component, and it's multiplied by 1 automatically because its coefficient is 1. It's 3 minus 393.5, and close the square bracket. As a sample calculations here, sample mathematical calculation, the answer is negative 119.7 kilojoule. Negative here indicates the whole process here. If it's negative, it's exothermic.